a lot of this stuff requires justification, and the justification is beautiful. Like justifying why the math is correct or why it is discussed in the way in which it's discussed. It can take a time. It can take time. So because of that fact, time can actually seem like it's getting out of your hands. But yeah, if all you do is just say this is the formula, this is how you use it, this is the formula, this is how you use it, then the mathematics becomes so dull and boring, and it doesn't even seem like this stuff is interesting. And that's my opinion, at least. I don't feel like math becomes something interesting when it's just like, here's a formula, here's how you use it, here's a formula, here's how you use it. But unfortunately, for the most part, that's what has to happen in classes. I don't enjoy that. I enjoy seeing why it is the way it is and how it was discovered. So sometimes I teach that way, but yes, time gets out of your hands if you do that. Deriving stuff takes a long time. Okay. So, okay, let's move here. We were talking about integration using vector functions. So let's say I have my R of t is defined as f of t, g of t, h of t. This implies that the integral from a to b of r of t dt, represent it as some like capital R of t, right? The antiderivative is evaluated from a to b. But that's just equal to component-wise integration. Okay. So let's do an example. Let's say R of t equal to 2 cosine of t, sine of t, and 2t. What is the integral of R of t? So before, that was an integral that had limits of integration. But this holds true for general integrals as well. So it doesn't really need to have a to b, even though we can do it if we want. So over here, this is the same thing as component-wise integration. So what is the integral of 2 cosine of t dt? What is the integral of sine of t dt? And what is the integral of 2t? All right. So how do I know what the integral of 2 cosine of t dt is? So this is how we know. Let's take d dt of sine of t, right? What is the derivative of sine of t? Okay. Then what if I take the integral of both sides of this equation? Then fundamental theorem of calculus says that integral of d dt is just sine of t, right? So that means that the integral of cosine of t dt is what my sine of t is. And do integrals care about coefficients? No, they just ignore them. So that 2 comes out. So this is just like a 2 integral cosine of t, and we've derived that that's sine of t. So this becomes 2 sine of t, right?
It's all coming back.
Yeah, this is how I think about it. I don't memorize. I guess the only thing I didn't memorize, quote unquote, is that the derivative of sine is cosine and that the derivative of cosine is negative sine. But even that, you can kind of intuitively think about on the unit circle. How does the y change? The rate of change of y on a circle. is cosine. Because between 2 points, the y changes based off of the x. Okay. Now, by the same token, what is the integral sine of t? Yes, because let's say, what is the derivative of cosine of t? It's equal to negative sine of t. And then you take the integral of both sides. Fundamental theorem of calculus says that this equals this. And so what did you say that this equals?
Negative cosine.
Correct. Because you just got to solve for integral sine of t in that equation, and you get negative cosine of t. Don't forget your plus c's. Actually, in this formulation right here, one thing I neglected to note is that you can also get a plus c, which that's your like vector constant of integration.
So is that written like for each different spot in like for the x,
Yes.
y, and z, or just at the end of it all?
Excellent. Yes, actually, for absolutely certain.
And do you have to differentiate like C1, C2, and C3?
Yeah, this could be like CF, CG, CH, right? Where it was added component-wise, but then we broke it apart into vectors. Yeah, that's right. That's what your big C vector is. It's little, the constant integration for this one when you're done with it, for this one when you're done with it, for this one when you're done with it. Great question. Oh, and what's the integral of 2t? What?
2.
The integral of 2t? That's
Oh,
the
integral.
integral.
T squared.
Yeah. So integral, yeah, it becomes t squared because integral of 2t is 2t squared all over 2. Cancel, cancel. T squared. Very good, Jamie and Alexis. There we go. So there you go. We integrated it. And we say plus some c, which is our like vector of integration, vector constant of integration. So before we could have said, you know, plus C1 here, plus C2 here, plus C3 here, right? And not have this. But then we could have broken it into just this, just this, just that, plus our C, where capital C is defined as C1, C2, C3. See what I'm saying? Because vectors add, and they add component-wise, so we can break it apart, right? If this is something plus something, something plus something, something plus something, we can break that apart into 2 separate vector entities with entries in x, y, and z. Very good. All right. Oh, opposite way. Now let's do a integral with limits of integration. Defined limits of integration. Proper integral is what they're called technically. Oh, this hurts. Ow. Ow. Ah.
It hurts to erase such good math.
It hurts. Yes. My arm hurts. So how about we do the integral of 0 pi over 2 of r of t dt, where my r of t, let's say, is defined as, where do I show what it's defined as? Did I not write that in here? let's say it's defined as 2 cosine of t, sine of t, 2t. Okay, and we aspire to take the integral of this function. So when we take the integral of this function, this decomposes to the integral from 0 to pi over 2 of 2 cosine of t dt. This is the integral from 0 to pi over 2 of our sine of t. And this is the integral from 0 to pi over 2 of our 2t. Okay. So I'll do the easy one. And we should probably break it apart. So the integral of 2t, 0 to pi over 2 dt, we showed earlier that that's t squared, right? But then we still have to evaluate it from pi over 2 to 0. That's the other fundamental theorem of calculus. So this results in pi over 2 quantity squared minus r0 squared. This decomposes to pi squared over 4. And that's what we put right here. And you know, there's a plus c, but whatever. That's understood, and we can always set that c equal to 0. Oh, well, actually, with improper integration, the c's cancel. So. But anyways, on to the next calculation. Let's do integral from 0 to pi over 2 of sine of t dt. What was the integral of sine of t? Yeah. If I had not done that recently, I would have forgotten and had to rederive it. But it is negative cosine of t. And so that means we evaluate this. So I'll factor out the negative and just say this is cosine of pi over 2 minus cosine of 0. At pi over 2, what does cosine assume the value of?
0.
Very good. And what about at 0?
1.
Very good. So this ends up being negative 1, which is positive 1. Last but not least, let's do the integral from 0 pi over 2 of 2 cosine of t dt. What does this equal? 0 to pi over 2. So then this is the same thing as 2 times sine of pi over 2 minus sine of 0. What is the sine of 0? It's a 0. And what is the sine of pi over 2? 1. So this is 2 times 1, which is just a 2. And here we go. This is our answer for capital R of t. Let's see if the fellas have any questions in the chat. No, not so far. Okay. So of course you can, write this out as 2i plus j plus pi squared over 4k. Clearly you could write it out like that. This is what that really means when you put brackets. It's the same thing. Okay, that was the end of 10.2. Oh, time to move on to 10.3. Ah. So this is about arc length and curvature. So you guys recall, for a curve, you defined its arc length to be this quantity right here. The arc length of some curve, the arc length of some parametric curve, that is. Here's some curve, some parametric curve. So you guys defined some length from here, the arc length from here, let's say to here. This is my A, this is my B, right? We define this to be L. And if f of t parameterizes how x changes and g of t parameterizes how y changes, then we define our arc length to be the integral from a to b of our f of t primed squared and our g of t primed squared. So this was supposed to be in section, what section is this? 6.4. So notice that this easily can be generalized. So for a vector, it's on 3 dimensions. Again, now your length from here to here. Okay, you can now define that L as the square root integral a to b dt. Now you have 3 functions to work with. Because we're in Calc 3. Calc 3. 3D, yes ma'am.
If you have time, do you mind going over the 2-dimensional one in a YouTube video?
I would love to.
It's been a while. That's like Calc 2.
Yeah, this is a very cool. This is a very cool derivation. I would love to do that. Yes. Okay. So now that's out of the way. We could also say that this right here, this expression, is the same thing as just the integral from a to b of some r prime of t dt, where r is defined as bracket f of t, g of t, h of t, right? As it has been so far when we talk about it in general. So let's apply this notion to a concrete example. Let's say our r of t is defined as cosine of t sine t and t. So let's say we want to find the arc length of, so this forms a parametric curve, right? In 3 dimensions, this forms some type of curve. And if it has a cosine parameterizing the x, and it has a sine parameterizing the y, and it has t parameterizing z, clearly it's going to look like someone got a coil, right? If this was fixed at a value, then it would just form a circle, right, forever. But it's not fixed; it's arbitrary. So you get that you create a coil because of that, because it moves in the z. Every time t, every second, it moves, so it forms a coil. But if it never moved, if the z stayed fixed, it would form a circle. But because it's moving for time t, it traces out a coil or a helix. That's a great point. There are bounds on the ranges of cosine of sine, correct. They have restricted ranges of output. And yeah, that's why the coil stays finite. The coil has a radius. The helix has a radius, if you will. Especially if you project them all down, the coils, and project it onto a circle, it would have a defined radius. Yes, absolutely. So let's say we want to know, okay, in one complete revolution, what is the arc length of this coil? And that is actually this. Oh, I should put the prime in here and then square it. Okay, I'm actually interested in finding out this answer because, I mean, think about it. It's very interesting. Is this any different from the circumference of a circle of radius, whatever it has? Because at the moment, if we set cosine of t equal to x, sine of t equal to y, I get x squared plus y squared is equal to 1 by the Pythagorean identity, cosine squared t plus sine squared t. So right now, if we project it onto its circle, it becomes a circle of radius 1. That's what we have here. But it's really a coil of radius 1. But it's very interesting. Does the circumference change if we cut the circle and turn it into like a coil? Does it change at all? That's really what we're asking. This should, for all intents and purposes, equal to 2 pi r, right? Let's see. Let's see. It would be intuitive if it did, but counterintuitive if it didn't. And it'd be very interesting if it didn't. But it would also be very interesting if it did. Everything is interesting. Okay, so what is the derivative of cosine? Yeah, dt, derivative of cosine is negative sine. So move this to this here. So this becomes negative sine of t squared plus, what's the derivative of sine? This becomes cosine of t squared plus, what's the derivative of t? It is a 1. Okay, so we got this thingy over here. Notice that we've already talked about this Pythagorean identity. And it's actually apparent right here. The Pythagorean identity is just looking at us in the face.
What are you gonna do with the negative? Oh, never mind.
Haha!
You can't-
Right, yeah. Yeah, it cancels. It's as if they engineered that in this construction. It is as if they were so clever enough to have engineered it into this argument. That's a beautiful property of squaring something. Takes away negatives, if there is any. And as I've been hinting, what's sine squared t plus cosine squared t? It is a 1. So this is the same thing as just 1 plus 1. I put way too much radical up in here for just 1 plus 1, right? So that becomes root 2, but we still got to integrate it. I still have a little space here.
Can we change it into like a 1/2 hour situation?
Why not? But we really don't need to because it's not a variable. It's just a constant. Right now, we're just integrating the constant square root of 2. I could have called it 2 raised to the 1/2 power. Yeah, that's valid. But we don't have to. We tend to do that when we have a variable like t, because then the power rule of integration makes more sense. But right now, we're just integrating. So we just get square root of 2t evaluated at 0 to 2 pi. Make sense? That square root of 2 just comes along for the ride. It's just a constant. So bringing that calculation over here, I get square root of 2 times my 2 pi, which is my t, minus my 0, which is my t, evaluated at 2 pi and 0, respectively. So then this breaks down to 2 root 2 pi. Oh my gosh! Wow! I mean, look, when it was just a circle, what would be the circumference of a circle of radius 1? 2 pi r, but that's 2 pi times 1, which is 2 pi. What is the difference between 2 pi and this thing? Yes, precisely. It's the square root of 2. That is incredible. So we had to like add a square root of 2 of length.
It kind of reminds me of when you cut like a square by diagonal. You get like 1, 1, and 2.
Yes, you are 100% correct. It totally relates to that. It 100% relates to that. Because here's why. Okay? Geometry is why. So let's say you got a circle like that. When you pull this out, the difference from 1 and root 2 is how much that coil has to actually have that added length to it. That is precisely correct. Another way to think about it is that it's traveling on a cylinder, correct? The helix is, the parametric curve is traveling on the surface of a cylinder. So notice that I can create a cylinder if I get this and tape it, right? If I get these two ends and tape them, I'll get that thing. And then you do it again, and you do it again, and you do it again, and then you get that picture that it shows in the book, that coiled helix. So you are 100% correct that it reminds you of that because it's completely a consequence of that. That the diagonal of a unit square has length root 2. Take a look. Here's that coil I've been talking about. I like the picture where it's actually on the cylinder. Yes. Yes, I like this one. Where it's actually on the cylinder. Notice that if you get a cylinder, maybe it's made out of paper, you cut down one length and straighten it out, it becomes a flat sheet of rectangular paper. And so this whole argument works. If you guys like getting shapes and changing them in your head and moving them around, you guys would like the mathematical study of topology. And I encourage you guys to all become mathematicians and become topologists if you want. If you'd like. Peer pressure. Because then you get to do this stuff all day. You know what I'm saying? Okay. So that's incredible. Wow. That right there is enough to make my day. My arm doesn't even hurt anymore. I'm just so filled with epinephrine right now. I'm keeping that up there. Oh, it's so beautiful. It has to remain up there. Okay. So it's your book then talks about how a single curve, like the helix we've been talking about, can be represented by more than one vector function. So you could represent it as like a cosine of t, sine of t, t. But it's also stating that you could also represent it, for instance, with a t squared and t cubed. So that same thing could be parametrized like so. Okay. Does this have like a lot to do with lecture today? No, I won't go into the finer details of all that stuff. I'm maturing as a Calc 3 professor. But it just goes to show you that there's more than one way to parametrize a curve. Sometimes there is, sometimes there isn't. Okay? So, now let's say we have some arbitrary curve C. C is some arbitrary curve. And it is parameterized like so. By these continuous real value functions, f, g, and h. Okay. And actually, let's form like a restriction here. Let's say that t ranges between these bounds. Okay, because when we do the limits of integration, we want t to only vary between a to b. So we want just a piece of some arbitrary curve. We have some three-dimensional curve, you know, but we only want this piece from here to here of that arbitrary curve. So we can define an arc length function S of t. Okay. And this arc length function really is what we've been doing. Recall that we could have defined what I said, what we've been doing before as this. And don't forget to square it. Oh, and don't forget to square root it. Oh, well, then that's kind of a trivial. See, that would just undo it, right? That would just undo the square. Really, what we're trying to encapsulate here is like kind of like taking a magnitude, if you will. All right, actually, this is what we want to do because this is precisely by definition what we're looking for. Right? That's precisely what we're looking for. I want you to take the magnitude. Okay. Would you like some tissues? You okay? Yeah. All right. So, your book, now we can define arc length as this. Okay. So your book then says that we can define a differential amount of the arc length. And you guys know that the arc length is a function of t. So we can call it that. As long as you remember arc length is a function of t. The more t you go through, the more length you'll get. Okay. So it says it's often useful to parameterize a curve with respect to the arc length. Okay, so why don't we do that? Why don't we find an arc length off of a given parametrization? And we keep using this really fancy, neat one. I'd say this is like the prototypical, oh man, I hate to erase you. I'd say this is the prototypical parametrization because it's just so cool looking. Okay, let's talk about this guy here, our helix, a radius 1. Let's say with respect to arc length measured from here. Okay, so here's a different way of doing it, right? So notice that what is the value of the parameter here? If z is equal to t, this implies our parameter t is equal to 0. Then we want to define what is our ds dt. Well, we found that already. We found that. Recall, this is prior to integrating it. This thing right here is just doing the square root and sum of the squares part. And it's not the integral part yet. The integral part is what makes it into that 2 pi root 2. Right? Because then you ignore that root 2, then you do t, evaluate at 2 pi minus 0, you get your 2 pi root 2. Okay? So what it's saying is actually we could arrive at the same conclusion, but instead of integrating from 0 to 2 pi, this thing right here, we can integrate from 0 to t, because that really encodes this a to b or 0 to 2 pi part of our ds dt, which is the integral from 0 to t of this guy. Really, it's just another way of doing the same thing. But now we are doing it in terms of the arc length parametrization. Yes, ma'am.
Is that just to like generalize it? So that way we can go to anything, not just 2 pi? Because we're saying we're going to t, however long that is.
Yeah, I mean, t can equal 2 pi.
Yeah.
Yeah, it does generalize it. But the point of doing this thing is to say, okay, I can come up with a vector function for the parametrized curve, and then I can calculate arc length. Or I can actually come up with like a parametrized arc length function. So parameterize a curve with respect to arc length. Basically, you parameterize it in terms of arc length. Really, it's just another way of doing the same thing, where sometimes this way of doing it is more desirable because maybe the expression is more neat and succinct. That's just all there is to it, because we're going to rederive the same result. Because notice that then integral of ds dt, don't forget a dt here, you integrate that and you just get s of t, evaluated from 0 to t. Okay? But over here, that's the same thing as doing this. Right? So I just get my s of t is equal to square root of 2t evaluated from 0 to t. But then, you can set your t to be anything. So like last time, if we set it equal to 2 pi, we would derive that similar result, 2 root 2 pi. So this is just, your book is just talking about how, hey, you could do it this way or that way. And actually, if you were to just do a generalized integral, and these would go away, right? You get a plus c or whatnot. These would go away. And you can actually solve, let's say this is s, you can solve for t and eliminate the parameter. So now over here, you can understand what T is. You can eliminate the perimeter and get that. You know, all this stuff seems kind of weird, like why are you doing this? But what would happen in your definition over here is that now you don't have to deal with the variable T. Now, this is no longer an R of T, because I can convert T to an expression that only has S. So I get cosine of S over root 2, sine of S over root 2, and just your S over root 2. So it's no longer an R of T. It's an R of S. Okay, mathematicians, as you know, like figuring out how to do something in multiple different ways. Because if you have multiple ways of attacking a problem, sometimes one way is very difficult to approach it, and another way is much more simple and easy. So we like to have a myriad of strategies to be able to handle certain problems. It is quite possible that in lab, you will see why this might be a more useful formulation than just straight parametrizing it. Now let's talk about curvature. Curvature. It is quite the interesting concept, right? So, have you guys ever maybe cut an orange and then noticed that when you set the peel on a flat table that it doesn't behave like a flat thing? It like curves up, and whenever you squish it down, it does weird stuff, right? That's because the orange peel has intrinsic curvature in it. It's not flat, right? So let's define via calculus what curvature can be. So before we do it, we say R is some parametric curve that is smooth. What do I mean by smooth? I mean that it's like differentiable everywhere and it has no discontinuities, right? So it has no sharp corners, no regions of like where the derivatives would be undefined. Okay. Then we will talk about this vector, capital T of T. We already know what this is, right? What is this? What happens when you get a vector divided by its own magnitude? What do you get out of that? Let's say I get some vector A, and then I take.
Oh, is it unit vector?
Yes, ma'am.
Yes. Sorry, I was so proud. I was like,
yes,
but it's like not coming out.
That's okay. Yeah, I'm very proud. Yeah, so when you get some vector and divide it by its own magnitude, you get a vector that points in the exact same direction as A, but its magnitude has been contracted or possibly expanded to 1. Notice that that's what we're doing here. This capital T is defined as us doing that to the derivative of our smooth parametric curve. So we got some curve here. We got some R prime of T to that curve R of T, right? And we're in 3 dimensions because this is Calc 3, baby. All right. So that R of T is a tangent vector. But then this capital T would possibly be a unitized version of it, Points in the same direction, but it has magnitude 1. It might be contracting it, it might be expanding it. Just depends. So curvature is defined as this. Define this kappa. It's a vector. It's defined as this. It is a derivative with respect to arc length of this capital T of us that we have right here. Very interesting, right? Very interesting. Let's think about that definition here. That is the same thing as this, right? Is it not? And that is the same thing as this. R prime of T over its own magnitude. So this is the same thing as dr prime of T ds scaled by this. I'm running out of room here. I need some more room. There we go. This is the same thing as d r prime of T ds scaled by this 1 over the magnitude of r prime of T. Now we know magnitudes ignore scalars, so they just become like this. I believe this was a theorem you guys had to prove or something like that. So really, curvature is being scaled, right? It's scaling something by this 1 over r prime T, but really it's the rate of change of the derivative of this r with respect to its arc length. Unit vector, yes. Yes. So think about that. This is our r prime of T, right? At different points, it changes. So it's talking about curvature. You know, we think of curvature, you know, what's something really curved, right? Like a sphere. So if you slide a little bit on the sphere, you'll slip off. But if you slide a little bit on the table, nothing will happen. So that's why this tangent vector encodes the abstract concept of curvature, because it says that if your tangent vector is through minute differences in arc length, like from here to here, if its position and where it points changes rapidly, then that you must be located on a highly curved surface. But if this vector, you move a little bit, it doesn't change very much at all, then you must not be on some surface of a high degree of curvature. Oh. It's that quiz that we had. We're out of time, but it's that quiz that we had last time. It's got us in a rut where we're like halfway in between sections. So we'll have to make up for lost time on Wednesday. And then Wednesday evening, you guys will have your fun exam. I will provide some questions that are like, hey, these are some good questions that might be like the exam. What I could also do, I really love doing this, is adding bonus problems to tests. Yes. I love that. As a student, if there was ever a bonus problem, I love it. So you can't get over 100 on the test. If you get the bonus problem, everything else right, well, you should get 100. But yeah, you don't always get everything right. So it helps to have that bonus problem. Maybe I'll put a bonus problem or two. And they'll be hard, okay? They'll be harder than the test problems because you have to earn those extra points. Okay? But yeah, I love getting access to more opportunities. Okay? I love that. What I would say is really understand what the sections are talking about. Those practice problems in the sections really set you up for doing the homework. We talked about this the other day. Alexis, I don't think you were there, but Caleb and Ivor were there. That you can find these problems on the internet. It's pretty easy. I won't tell you how. I won't tell you where. But you already probably know you could find access to this information. That's fine and dandy, but you have to know how they're getting those values, right? And you have to attempt these problems without looking at the solutions for an extended period of time. So with that being said, I don't feel as terrible of a professor that I haven't given you solutions to all those sections yet. I really planned on doing it, but it just didn't, the time didn't work out for me. So what I will do is I'll upload selected solutions to problems that I think will be very like what will be on the test. And I'll give you pointers on 9.1, 9.2, 9.3 problems that I think will be really likely what will be on the test. And we'll go from there. This is our first exam together. We'll see how it goes. If I generate an unfair exam, then we will make it, we'll do something to make it fair, okay? If I do.
Will there be any like theorem questions so far, are you thinking? Like prove this, prove that?
Oh yeah, how to prove something. Right. That might be a bonus question. You never know. I may ask you to prove something for bonus question. I might give you like 2, 3, maybe even 4 bonus questions where it's like, try to prove this. And even if you don't get to full-blown proving it, if you're attempting it and you're really close and you're doing good mathematics, you're going to get partial credit for the bonus. So let's say I have 3 or 4 bonus questions and you get partial credit on all of them. Let's say you don't get any of them right fully, but you get partial credit on all of them. That might give you like 2 problems worth of like bonus points. Sound good? Yeah. I really am proud of all of you all and want you all to succeed.